Okay, so in this lecture I'll be solving some examples for you to illustrate some of the definitions and principles that we have covered last time in the online lecture as well. So before we go there, I've got a question about the application of the HVAC or air conditioning. How is it really related, or some of the more applications for that domain? How is it related to fluid mechanics? So I'd like to go over the this example right here. Let's imagine we have this room, and you might have a split unit, which is, or the window type air conditioning system, or you might have the diffuser, where you have the air coming in from, it might be from the roof, it might be from the side, but let's just make it simple, where we just wanted to discuss some fluid mechanics principles. And mainly I want to discuss how's that really related to the continuity, or we haven't actually called it continuity yet, but we have covered last time the mass conservation. So let's look into this diffuser from the plan, the top of the room. Let's assume it's square in shape, and then you have this, so they have designed a specific size, and then you have this door. And now somebody actually is sitting here somewhere and he feels cold, so he decided to get half of this, let's say, blocked like this. You can cover it with, for example, some tape, anything that, but anyway, so the area is actually now half the initial area that you have. Okay, so now you have almost half the area. If the system, remember there are some other rooms that are taking the airflow rate, so if it's well balanced, then the same amount of air would still go through this. What would happen is you will start hearing some noise. Now why is that? It might be pretty simple for us as of now, and it might get complicated actually as we start looking into the equations and why is it. And it's mainly, remember that when we go to Bernoulli, remember this example if you want, ask me again to try to relate what happens here. And basically it's like you reduce the area, so you might think, oh, is the pressure higher, like a nozzle when you put your finger on the hose, so you have higher pressure? Maybe. Kinetic energy higher? Yes. The area is less, so velocity is going to be higher, so it makes more noise, especially with air. So we will be looking into that, and how's that related, like area and velocity. And this is what we actually call continuity, and we will look into that in more detail. So I just wanted to go over this example. Also, another thing is if we increase, if the door was closed and we put more CFM into the room, what would happen, for example? Or if we close the door and then we seal, for example, this very small gap here, and all windows are sealed, and then people complain that they're actually feeling hotter inside the room. Why? It's a closed room, very well sealed, and then you have decided to close this, and then all the air coming in, it keeps coming in, and it starts becoming like pressurized till the moment where the pressure here is higher than the pressure inside the ducts or the supply, so the pressure of the room is higher, and then no more air can get into, because the pressure here will be resisting or preventing the air from coming into the room. And then you don't have enough cold air coming, and then the temperature of the room will start increasing, and then you'll start having this warm sense. Okay, so enough with that. Let's go into some more examples related to the dimensionless or the unit system, and the last topic, which was pressure. We have solved pressure, so I don't think I'll be going over that, and then we'll go over the other fluid properties, which are the specific weight and specific gravity. So let's start with this example. We have the drag force. If you don't know what's the drag force, it's just kind of force, and it's related to the design of cars, airplanes. So there's a drag resistance of air. For example, you might have a structure here. Let's say it's a boxed bus or car. Anyway, so there's a drag force or resistance here, and this force is actually when they work with a fluid, they put it in terms of a coefficient called C sub d, which is the drag coefficient, times other fluid properties, which are half rho v square times the area, or as they have arranged it here, rho v square times a, all of it over a. But that's basically that's the kinetic pressure here, half rho v square. Don't know why it keeps going, the pointer there. And then if you multiply pressure times area, so that's a force, and then you have part of that related to the how we can transfer that into drag force. So that's called the drag coefficient. That would be the final chapter in this course. So we don't have to understand this equation so far. All what they are asking us to do is to verify or try to find the dimensions or the units for the drag coefficient CD right here. Let me change the color here. Sorry for keeping the color all red. I like to use some colored notes. Okay, so V is the speed of the wind speed or the speed of air. Rho is the density. A is the cross-sectional area, and then CD is the drag coefficient. So we need to find CD in terms of the other parameters. So how we can do that is simply by rearranging this equation, and I think I have it here, so let's erase that. Let's see if we're good with this. No, let's just erase it all. Okay. So what we have now is we have that equation, so we're going to rearrange that to have the drag coefficient in terms of the other parameters that we know, which are the force, density, velocity, and area. So if we know what's the dimensions of those, we can then get CD. Remember, there's the primary units and then there's the secondary units. All of these are secondary units, kind of, so if you don't know how to derive them, you can always go back to table 1.1 in your textbook. So the force is essentially F or MLT minus 2, and the density is mass over volume, so it's ML negative 3, and it's somewhere here and I can't see it. It's right here, that's the density. And then we have the velocity, which is distance over time, and that's going to be, if you don't know how to derive it, you can look it up from here, right here. And then finally the area is simply, we can say it's rectangular, it's circular, anything, if it's circular it's pi over 4 d squared, so it's going to be L squared. If it's a square, then it's side times side, so it's L squared. Remember, we're not trying to find the exact answers and values, we're just looking into dimensions and units. So now we take all of these and we substitute them into this equation. So CD is going to be now 2 is a dimensionless number, so we can drop it, and we will have the force, it's mLT minus 2 divided by the density, which is mL negative 3, and then we have the velocity square, so L squared T minus 2 squared, and then finally we have the area, which is L squared. So this square with this square, that's 4 and negative 3, so all this goes, and then we have one of them, it should go, so I'm gonna cancel this, and we have L left, but we have another L here, another L here, so they cancel out. The mass here and the mass right here, they cancel each other, and then we have t to the negative 2, it goes with t to the negative 2, so we're left with unity, so no dimensions, or it is a what we call a dimensionless coefficient, such as the friction factor, friction loss factor, and other parameters that you might have. Okay, now if you have questions, you can always come back and ask me. You can come to my office, or you can ask me next lecture on Monday. Hopefully you're watching this before Monday so that you can come back on Monday. Another example is to find verify the dimensions in both FLT system and MLT system of the following. First, frequency, stress, strain, torque, and work. So we'll start with frequency, and we need to know some physical definitions, like what is a frequency? It's 1 over time, right? Or it's cycles per time, per unit time. And then we will go to this table, table 101, 1.1, and we can pick the dimensions. So cycles is simply, it's a number, so it doesn't have units. And then we have time right here, and it's simply t, so it will give us the frequency t negative 1, and that's what we know, 1 per second or 1 per minute, etc. Next we have the stress right here. Stress is equal to what? Stress is like a pressure from strength of material. We know that it's going to be force over area. So now we need to find the units for the force, but since they have asked us to find the FLT and MLT, so we're going to leave this force as F and then divide by the dimensions of the area, which is again L squared, as we have discussed in the previous example. So it would be FL negative 2, and we're done with the first unit system. But they're asking also to find the MLT, so we need to transfer this force into a MLT system. And we would go to table 1.1 and we look up the force oops, unfortunately I can't see it. It's MLT minus 2. Let me try to fix. So if we put this, if we substitute this one right here, we notice that we have L negative 2 here and L here, so that will leave you with an L minus 1 and T minus 1, and we can't see it for some reason here. Yeah, that's because this one is overlapping the other one. So let's take the pen here. So if we substitute the F, M, L, T minus 2 times L minus 2. I don't like to do things just orally. It's better to see everything. So it would be M, L minus 1, T minus 2, and that you can leave it, or it's ML T squared. And let's double check. Let's see if my work is, and because we've just put the table here a moment ago, so if we look into the stress or the pressure, and we can see it right here, ML minus 1, T minus 2, so we're good. Okay, third we have the strain. What's the definition of strain? It's change of in length with respect to the original length. So what's the units? So we're gonna have delta L, so that's a distance by distance. So again we have L to the 0, or it's going to be dimensionless. And then we have the torque. So there are different ways to define the torque. One of them is you can look into the power divided by the RPM, or you can look into the more simple example. If you have a rod and you have a force and you have the radius here, so we know that torque is force times the radius r, or we're just looking into values here, so it would be force times distance, and that would be the force is simply F times distance L, and then we'll be doing the same exercise as we have done above. Force is ML T minus 2 times L, and that would be ML squared this time. That one was L negative 2 and L, so it gave you L negative 1 right here. This one is L squared, or L and L, so it will give you L squared T negative 2. And finally, work. Work is defined as force times distance, so it's exactly the same units as for the torque, except it's different physical quantity. That's work, that's torque, both are work, and that's it for this example. Let's go into another example, and I think that's the last example that I'll be solving. We'll see. So if P is the pressure, if P is a pressure, V is a velocity, and rho is a density here, fluid density, what are the dimensions in MLT system for P over rho, and then PV times rho, and then P over rho times V squared, P over rho V squared. So the first one is P over rho. Okay, so the pressure, we will have to use table 1.1. I'm not going back. You can go and check the units. And we have derived it just in the previous slide. It's ML negative 1, T negative 2, and then the density, it's mass over volume, so it's ML negative 3. So you would get ML squared, M with M, it will cancel out, and then you have T negative 2 divided by L negative 2, or you can say L squared over T squared, or L squared T negative 2. So it's kind of M squared over second squared. We'll see what that means later on. The second requirement, or second part, part B, is the pressure times velocity times the density. Again, we have the pressure ML negative 1, T negative 2 from table 1.1. And then we have the velocity, it's distance over time, so it's L T minus 1, and then we have the density ML negative 3. So if you do the manipulation for all these powers, so M, we have two M's here and here, so that's M squared, because that's a product multiplication. And then L, we have L negative 3, L, and L minus 1, so this one cancels out with this one, and you're left with one term, which is L negative 3, and then we have T minus 2 and T minus 1, that gives you T to the negative 3. I don't like to work with negatives, so I prefer to write it like this, but that's fine. Whatever you put, it's okay. Over LT all cubed. It's more compact. And then the last one, part C, is P over rho V squared. And we will see why I like this example later on in chapter 3, because these are some of the terms that you will be seeing in Bernoulli's equation. So again, P is M L negative 1, T negative 2. Then we have density, mass over volume, and then we have V squared, which is L T minus 1. I wonder where's the squared? Where'd it go? Oh, there it is. Okay. And let's... if I just waited. Okay. So it will give you M with M. They cancel out. And then L negative 1 with L. Remember, there's an L squared here and L negative 1 here. So he will be L negative 2 and then L squared. So they also cancel each other. And then you're left with T minus 2, T minus 1 times 2. So they also cancel each other. And you're left with nothing here. So that's a dimensionless term as well. Okay, so we're done with examples for the unit systems. We will jump into the second part, which was the density, specific weight, and specific gravity. So in this example, we have density of a certain type of jet fuel is 775 kilogram per meter cubed. Determine its specific gravity and specific weight. Now, you still remember what are the definitions? So specific gravity is density of the fuel by the density of water, whereas the specific weight, or gamma, it's rho times g, or it's m by the volume. And density is simply density, it's mass. Density is the mass per unit volume. Sorry, this is weight, not V. Weight per unit volume, it's specific weight. So let's start. We have the density of that fuel. So the first thing, if you look into this definition right here that I've just written, it's density over density of water. Now we have the problem, it's given in SI unit, so we're gonna solve for SI unit. Now the density of water is they didn't really give us, so I have chosen the 4 degree Celsius, or you can use the 1000 or 999 kilogram per meter cubed. It won't make a big difference in terms of the answers. And that's the density that they have given us. That's our reference for most of our calculations here. The water, not just the density. We will see also for specific weight. So that gives you 0.775. Okay, now also the specific weight, as we have said, it's the density times the gravity. The density, we have it, it's 775. So we need to know the gravitational acceleration, and that's 9.81, and you will get 7.6 kilonewton per meter cubed. Of course, it would be actually 7600, but then we've divided by 1000 to get this kilonewton pulled out from the answer. Okay. So again, if you have questions, again, you can ask at a later time, but I hope you can watch it before next week. Okay. Now in this example we have a soda can, and it has 335 milliliter of whatever it's containing, Sprite or Coke or I don't know. The mass of the full can is 0.369, that's the full, 0.369 kilograms, and then the empty can weight is that, yeah, that's mass, whereas the weight of empty tank is how much? 0.153 newtons. Determine the specific weight. Again, we need to know gamma and specific gravity Sg of the pop. So we need to know that for, and again, those are for the fluid, not for metals. We're not dealing with metals in this course. We're dealing with fluids, so no solids. And compare your results with the corresponding values for water at 20 degrees Celsius. Let's first find our answers for the specific weight and the specific gravity, those two here. So the specific weight, as we have said, it's the weight of the fluid divided by the volume, or it can be density times gravity. However, I don't have the density this time, and I don't have the specific gravity to find the density of the fluid as you might think of, but we do have some weights given here. So let's try to figure out because we do have the volume given to us, so let's try to find the weight of the fluid, which is simply we have the full weight or the full mass of the can, so that includes the can itself and the fluid, and then we have the empty, so if we subtract those two from each other we would get the weight of the fluid. Weight full minus weight of empty tank. Okay, so the total weight, we have the total mass 0.369 kilograms times g, 9.81 meter per second square, so that would be 3.62 newtons. And then we would substitute that right here in this equation, right here. So you would get the volume. Okay, let's move on. So gamma as the full weight, which is 3.62 right here, this one, minus the empty weight 0.153, that's in Newton, and then we divide it by the volume. The only thing is the volume was given in milliliters, so we converted that to liter. We divide by 1000, and then from liter to meter cubed we divide by another 1000, so that would be 10⁻⁶, and then you would get 9770 for the specific weight. We know for water it's almost 9.81, but they gave us this 20 degrees, so we have to check at this specific temperature to make our comparison. We'll do that just after we find the specific gravity. Okay, so now to find the specific gravity, which is, as we've said, it's density over density of water, so we need to find the density of the fluid. So we'll be using this definition now. We know that gamma is rho times g. We have found gamma here, and we know g, it's 9.81, so we divide that by 9.81, and we would get 996 for the density. Then we take this number and we divide it by 1,000. We will get 0.996 for the specific gravity. Okay, so to find the water temperature, you can't use the water properties at 20 degrees Celsius. We can't use the values from the tables on the cover page of the book. We have to go to Appendix B, where we will be going and discussing that in more details, but whenever we have some specification for the temperature, we have to go to the appendix at the end of the book. So if you look into the numbers there, you have the specific weight is 9789, the density 998, and the specific gravity is 0.9982. Here it was 0.996. Oops. 0.996. This one I forgot. 9770. And then the density was 996, I believe. Yep. This one was 996. So you notice this one is less than this. This one is slightly lower than the values of water at 20 degrees Celsius. Okay, and with that we come, I would like, since I have a little bit, some more, I need 2 more minutes to discuss this thing. What's the importance of, I didn't focus on this a lot last time, importance of the specific weight gamma. So now we can actually have tables, and we will see that throughout the course. We can have tables for different fluids, for example oil, a fuel grade 1, grade 2, grade 3, and then we can do experiments and we start reporting the specific weights, such as the specific weight for water. We have that, but we can have those here reported for us at specific temperatures, or the more useful one is actually SG, the specific gravity. Now this you have to specify the temperature, because remember, gamma as rho times G. Now G, we're on Earth and we're assuming it's constant, almost 9.81. We're not gonna really discuss the variation in G, but this one, if you have a difference in temperature, then the density is going to change. And the reason that this one is, it depends on the units is the units or temperatures, is that because it has some units here, which is kilonewton per meter cubed or pound force per cubic feet. The nice thing about SG, and you will see that in many courses, is that we like to work with dimensionless groups. So if we can determine the specific gravity of oil, all what we have to do is simply, I would tell you, find, for example, whatever value, for example, the specific weight at 20 degree, 100 degree, etc. So you don't have to go and find the specific table for the oil, or what you have to do is have one table which is for our reference, which is for water, because we know that specific gravity is density by density of water. So if I give you this value 0.78, or for mercury or whatever 13.6, all what you have to do is you have to find the density of water at that specific temperature. If I give you, I want the specific weight, then you can multiply this times G, or you can simply divide this by the specific weight of water at that temperature, and so on. And we need this actually to find pressures. For example, we need gamma to find the pressure of a specific liquid. in a duct, which is, as we have seen in one example, it's rho GH, or rho G is simply gamma times H. So now if we have the height H, all what we have to find is gamma. To find gamma, all what we have to have is the specific gravity of the liquid. So if you have a duct, I'm going to conclude here. If we have a duct and we have a manometer here, and you have the height H, and you know what's the specific gravity of the oil or the fluid here, so we can use the specific gravity here to find the specific weight of the fluids, and then we take this, because we know that this one is 9.81 kilonewton per meter cubed, this one. So I'm giving you the specific gravity, so you can find gamma and you can take it and substitute it in this equation times the H that you read it, and you would get the static pressure of the fluid right here at this point. Okay, I'm gonna stop here. Again, I do recommend watching these videos and take some notes. If you have questions, just put it there. If you feel you can't continue without asking that question, just take a break, come ask me if you're on campus, or just wait a couple days till you can ask me, and then you can continue watching the videos. But for now we will stop here, and we'll pick it up next time with viscosity, and we'll start that in class. So have a good day and enjoy the rest of your day and the weekend if I don't see you before then.